So today we will look at Schauder estimates. T2 alpha estimates. There are also C1 alpha estimates. I will mention that in the end. And like my previous talk, to focus on the ideas, I will only look at this equation. And then I'll mention what the suitable modifications you need to do to get coefficients here, okay? And so the result we're looking at is if f is in C alpha, then U is in C2 alpha. We'll actually prove something much more than that. We will show there is a notion of Schauder. I mean, what we'll show is that if there is C alpha at a point 0, let's say, then use C2 alpha at that point 0. But this may not make sense to you, right? Because to differentiate, I need an open neighborhood, right? But this will be made clear soon. Okay, so let us start by asking what is Schauder regularity? Right? What is? I mean, you know the definition, but what does it mean? So let us say I have some function, right? And I want to say it is Schauder regular at a point. What that means is if it is Schauder regular for alpha, it means I can do this trapping. Let's say some x0 at some level cx0, which here you can see from the picture is like x0, right? But let's not mention that. Then with the uniform opening, okay, the uniform opening is important. I have, let's say, Schauder alpha, and then what is this? This is translated by Cx, right? And what is important is, if let's say if I say that it is Schauder in this interval, okay, say it's Schauder in this interval, that means I can take this graph, take this trapping, and move it along this graph, okay, and this graph will never cross this. This is what Schauder is. So maybe a Lipschitz example would be easier. Schauder may be harder. So if you remember in Agnes lecture, he said something about cones, right? So if something is trapped between cones uniformly, it's Lipschitz, right? So let us see a simple counterexample to make sure we understand. So what is something that is not Lipschitz? So I don't know. X squared in R. This is not Lipschitz in R, right? As the derivative will go up, right? What this means is, let us say I take this is x squared, right? This is x squared, very bad picture, but and if I want to cut it at some point, so let us say I was only focusing on this interval, then you know in this interval derivative is bounded, it's Lipschitz. And in fact, if you just take some cone here which traps this thing and slide this down all the way to here, right? Then this graph will never cross this cone over, right? It will not curve so much, it will cross the cone. So you can just slide this. So if I confine it to a finite interval, I can trap this graph between these cones. Is this clear now? Here the cone is just like two straight lines, right? But in higher dimensions, you understand how this goes, right? Whereas, let us say, but why is it not Lipschitz? Because the derivative keeps going up. So let us say I kept translating this cone upwards. So eventually what will happen is, because it curves so much, at some point, I will no longer be able to trap it. So at some point, the graph will go like this. So I will no longer be able to trap it because the derivative goes very fast. Okay, because this has some fixed derivative. So this is why this is not Lipschitz in R, but it is Lipschitz in like a finite interval. Now this is so this is C alpha. Okay, I mean you trap it between this sort of a thing. So the difference is this one lets you have some sort of gap here. This one is narrow. That is what this is. Okay. This is clear, right? What's happening? Okay. Similarly, let us ask what is C1 alpha. Okay. So what do you think it is? I do this, I have some function, right? Let's say I want to look at C1 alpha at this point. Then I have the tangent plane here, right? From up and down, I have the tangent plane here. Now let's say this time, so this is let's say some, I'm at some x and this tangent plane is Lx. What is Lx? Is the value at this point as a gradient at this point minus another function, right? So there is some sort of distortion here. The picture is bad, but okay. I don't give you a and here. And this is Lx. Now earlier I lifted the point, lifted it from the point. I will now lift it from the, let's say, some universal constant. But of course here, since we have this is flat, this is one more order. So the picture is not exactly accurate. But you understand, right? So I can lift this plane up. I can open this plane up by this amount. And with this uniform constant, as I slide these, my graph stays between them. So this is C1 alpha. Okay? This is what C1 alpha means. And this will, of course, conform to the usual notion of dux minus dy is less than equal to x minus pi per alpha. So and similarly, C2 alpha would be I have a paraboloid up and down. And instead of a separation with at 1 plus alpha, I have a separation at 2 plus alpha. And the separation happens with a constant rate. Okay, and the rest of the graph is contained there. That is C2 alpha. So, pictures are nice and long. Yeah, maybe I'll do a C1 alpha. Okay, let us look at C1 alpha. So suppose U is C1. Suppose I have U in C1. Then this picture is grad U is C alpha. Okay. You should this condition I'm assuming to make my life easier. Why do you think this is? Like, do you have any insight? How do I translate this picture into a proof? Okay. So you rescale, right? You take, I mean, I just have some, look at some points and they have a distance, right? And these are some points. I'm sure that ux, grad ux plus grad uy has some bound, right? So x and y nothing special. I can always do something like x, y, and I can always put a 0 between them, which is to make the pictures look nicer when you write pictures of pictures. Then what this picture means is that u minus lx in a ball of radius, let's say r, right, is some uniform constant r power 1 plus alpha, right? That is what this picture means. For every x, you have this. Maybe since I've taken x and y here, maybe I should just put it here. Right? For all z, this is what this means, right? That picture. U minus lx is separated at that rate. I subtracted off the lx, so this is the rate, right? Now, I mean, this Lz, as you know, has the gradient setting in it, right? So if I look at Lx has the gradient setting in it. Ly has the gradient setting in it, right? So I should ideally look at this difference, right? If I take this difference anyway, since I'm looking at a point, pondered about a point, that goes away. Now, thing is, I would like to rescale. So I will rescale linearly. Okay, what this rescaling means is I'll write f r of x, f rx, right? I do a linear rescaling. So if you do that, now this notation is clear, right? What I mean. If you do that, then 1r comes down. What do I get? Lxr minus Lyr. In L infinity, now since I've rescaled, what does Br become? B1. One rescaling takes that factor off. And I get R bar alpha, right? Now I have, so this is a plane whose L infinity norm in BR is like this, which means that the coefficients of this plane also have to separate at that rate, which will imply okay, I mean, what should be precise? What I'm doing is grad ux minus grad y is right. Okay, this is clear. Is this obvious to you? Why bound on the polynomial or on the, this is a linear polynomial, you will have a quadratic polynomial later. Why a bound on the polynomial in the ball, L bound, translates to a bound like this? Okay, I'll talk about it in the end. I will just think about it. It's not entirely obvious in the first answer. All right. So I hope I've convinced you that you can do C2 alpha, etc. by pictures. Yeah. So similarly, let me just write something. So I'll assume that U be C2. Then U is C2 alpha. So there should be some lobes, there will be some balls in small. We are in smaller balls. We are doing all interior, so it's big ball, small ball.
So what's on the right hand side of this last line?
This will be your
last line.
Right.
Yes.
If this is small, this is this. If this is too large, anyway, it's to dominate this, right? So I didn't want to say that, make that argument side of this. Okay, so the other thing is, I was saying, yeah. So we are doing interior stuff. So there'll be big balls, there'll be small balls, and there'll be constants which will be flying around. So please excuse that. Okay, so then use C2 alpha in, let's say, the domain omega. Some domain omega. If and only if there exists a parabola, right, or a quadratic polynomial, whatever you want to call it. Px, okay, which may be at y is some ax, which is a real number, times some vector bx y minus x. This is like a gradient, right? Plus y minus x acting on cx, which is like a Hessian or your curvature matrix, a matrix, right? So it is something like this, okay? Such and what's most importantly, and a uniform constant k such that u minus px L infinity d r x. So this x and this x point with less than or equal to a. So it's separate. There it's separated at the 1 plus alpha. If I have quadratic or crossing quadratic, it should separate at r plus alpha. Okay? That's the definition. Now going from here to here, there's a similar argument involved, except instead of linear rescaling, it's into a quadratic rescaling. Okay. I should mention something about this constant, which is that at some places, I think online I found people have written this or this, let's say, and then divided by r, okay, and said u is C1 because it looks like that's how it should work, right? Derivatives, but that cannot be correct, all right? Because you look at, I don't know, you look at any rate that you want and add any wild oscillation that you want. This is not even C1, right? Forget about being C1 alpha. This will satisfy something like this. The problem here is that this constant is not uniform. As you go close to the origin, the constant goes up because the derivative is going to go up. So you should be careful. No? Don't just divide and say it's differentiable. It's not. That is why I started with C1 and C2. Okay. Otherwise, there's no argument. That otherwise you have to start with the C0 solution and climb up the regularity, which I don't have time to do. So, which is why I'm starting with C2. Okay. This is okay, right? Let's constant better uniform. And if your proof is not using the constant uniform, there's something wrong. Okay. So yeah, so as often, so this is very nice and neat. And if you look at this, let's say if I forget about the domain, right? This has nothing to do with the domain, right? This is a point-wise condition, right? So which is what I meant when I said that we have at 0. So what this means now is that if you have f is Helder continuous at x, okay, then at that x you can always find a second order polynomial which will approximate u in that sense at every scale around x. So any ball around x, you have a polynomial which goes at the rate 2 plus alpha. Okay. So in this notion, there is no, I mean, you understand this is a point well known. This has nothing to do with whether I have a differentiability, whether I have differentiability in open set and so on. But it so happens that this notion, if you have it in the full domain, you can recover C2 alpha. Okay, but this seems more general, right? At the first glance at least. So this is what I'll then do. And one more thing. So like I said, you have on a paraboloid, you have control, okay, in a ball, which then it translates to control in the coefficients, which means that the coefficients in particular contain the d2u and so on, which means that this gives you all your bounds. Your C2 alpha bound would be something like this up to a constant factor. The constant factor will depend only on the dimension. And maybe I should mention now, why this is so is because finite dimensions on finite dimensional vector spaces, all norms are the same. So this is, you have to use that in the proof. It's not obvious, like, as in obvious. So that needs to be used at some point. I'll not go into that. All right. So that is that. And as often happens, so here, I said what I want to say. Yeah, as often happens, this is a very neat condition. Point where I have this, but I may not have this, right? I may have a sequence. That is what often happens because we construct things. So that is just a small proposition. Suppose we can find a sequence of paraboloids pk at x, ak, which is a real number, which is like the pointwise, which is like the value at the point, k, which is a vector, which is like a gradient, which approximates the gradient eventually, and put a half, as you know, just for convenience, like for second derivative, x, mk at x. This mk is a matrix, it's like your Hessian, right? Okay. And such that RG is equal to uniform constant. Okay. Then alpha at 0. This notation I've explained now, right? What it means with constant. I mean, so the constant, like I said, will be just up to some dimension factors, right? Okay, and there is some estimate here which I'm not going to go. All right. So what this is saying is, instead of finding a polynomial which works at all scales, at every scale, this is the scale, right? So you have 0, 1, r is somewhere here. You go like this, right? I don't know. You do this, right? So if instead of having a polynomial that works everywhere, if at all scales I can find a polynomial such that it still respects this rate, I'm good. Right? And I think this is very standard, right? If you have some case statement like translate something like this. In any case, wait, do I have to prove this? Again, you look at quadratic rescaling. So for me now, FRX, a generic function is defined as alpha minus 2. Okay. Then, see, let me just give the outline. This says that I have bounds on the coefficients again. The coefficients have geometric, it goes in a geometric fashion, so they'll converge. That's basically. But then the alpha is positive. This is neat. This is alpha, so you have geometric range, and I'm going to use this one. Okay. So yeah. So then k plus 1 minus pk in L infinity b and gosh. This is k plus 1, as you know, is mistakes there. So instead of writing L infinity, I'm just going to write a radii. Okay, the sun. understand what I mean, right? L infinity RK plus 1 plus one. Now this there is something like 2 K R okay. Which means if I do the quadratic rescalings, this is P K plus 1 R, this is a rescaling. P K R quadratic rescaling is less than or equal to 2 constant R K alpha. Right? Right? Because this 2K will go here. I'll do that K plus 1. And this is in, since I've rescaled, so then V1. Okay? So I get this estimate here. Next. Now we are done. So now that I have this, I have a bound on a parabola or on a quadratic polynomial in V1 in L infinity norm. This translates into similar bounds up to a constant on the coefficients, right? And why is this again? Because this is infinity norm, there's 2 norm, but they're all the same. So the vector space of polynomials and all that, right? Okay. So therefore, by whatever I said, AK plus 1 minus, so there should be some rates. So the constant, there is no rate in front of it. So what rate, at what rate should it go? Maybe I'll start missing constants. Okay. Is this clear why this goes at the rate this? Because I don't have, because this constant does not have a rate. When I write the meter on rate. And what do the, at what rates do the gradients or the approximations to the gradient converge? Okay. And at what rates should the patients go? Is it okay now? These are the rates. Now it's okay, right? What's happening? Okay. So these are all, this is difference and this is going geometry. So I compare it with geometry series or this is Cauchy, however you call it. And therefore, EK goes to P infinity, which is A plus bx plus half x. Where this is what? This is what MKs go to. This is what BKs go to. And this is what AKs go to, right? So this is really A infinity. M infinity. And they all go at these rates. So this fastest, worst. Okay. All right. And then you're done, right? All right. So 2 minus P infinity B R power K is equal to U minus PK minus PK plus AK minus A. The rate at which this goes is BK minus B. The rate at which this goes is 2K MK minus. Right, because I'm back to this. This is in which is up to a constant that depends on R actually. R and some key that T plus that. So now you have it at these steps. Right? So if I have something in between, standard, right? I have to do it. So I can get from here, right? Alright, so this takes care of this. So now I'm left with the last bit, which is very simple. So do you think if I put alpha is equal to 0, I can recover C2? Sounds reasonable, right? If I have alpha is equal to 0, then it's separating at a quadratic rate. So it sounds reasonable that I should get a paraboloid regardless. So any guesses? These are just minor points, it's not relevant to the flow. You don't actually get C2. You just take, I don't know. What's this one? You take some test form that truncates or your quadratic, or you construct functions like this. This is basically just something like 1 to b half. Yeah, it's 0 into b1. You know how standard construction, right? Then, if you truncate this at level n, you will always get the approximation of level n, but this will not be in C2. I don't have time to compute, but you can check. So alpha is equal to 0, you will not use C2. Alright, so we call this theorem 1. Theorem is clear, right? F is C alpha at 0, then U is C2 alpha at 0. Alpha at 0, I've explained it. So, like I said, since we have the Laplace, we have the harmonic estimates for free. When you don't have the Laplace, right? If you have some other operator there, you have to measure its closeness to the Laplace in some sense. All right. And similarly, I've taken F in C alpha, but you can weaken that condition to something like C alpha in ln norm. Okay, but again, I don't want to go into that. And those are, like I said, cosmetic changes. Okay, the main idea is what I'm doing. Those things are just technical. You can go to step. Okay, so first of all, I can always assume f of 0 is 0, right? Why is this so? Because I can always subtract off a parabola. So I think 1x squared, 2n will make it 1. Times. So if I do this, I can always assume 0 is 0, right? So this is a standard thing, so I don't want to say more. 0 is 0. And as I did in the previous one, I can make norms as small as I want, since that's scale invariant norms here. That's a combination. But I don't know. So maybe looking at, I want to make epsilon u infinity norm small, so I should divide by u infinity norm, right? And maybe I'm in B1, so everything is in B1. Let's say. Plus, I want to make the norm of f also small. Okay, so I'll do 1 by epsilon. And this epsilon is in my hand, right? So we shall choose the C alpha norm. B1. If I multiply by this constant, right, I can always ensure what? I can always ensure that L infinity B1 less than or equal to 1 and F C alpha, the whole thing. I can always ensure this, right? So I'll always assume this, which means I'm reduced to proving what I want to prove in this setup, where epsilon is in my hand. Okay. You'll see what's really happening with this. So this is the same thing as when I did the W2P estimate. The right hand side becomes smaller and smaller. You get closer and closer to harmonic function. You have to quantify the whole thing. Okay. Except there we did it in terms of LP spaces. We had to go to maximal functions, but here it's much nicer because we are working with healthier estimates. So we have point-wise estimates. So it's quicker. You don't have to go through ad hoc instructions. Okay. Let's see. So I will choose this data. As long as I choose epsilon in a way which does not depend on you, I'm fine, right? Because ultimately estimates true. Okay. So step 1. Step 2. So what should I do? I want to say it's close to harmonic function, right? So since I'm working with an explicit operator, and so I mean, so everything is explicit for me. Always just construct harmonic function, right? So this is standard thing. This is what I did last time also. So I'm hoping that this time it's not coming out of the blue. Maybe last time it came out of the blue if you're not used to it. Okay, so then what does V minus U solve? So if I look at U minus W, this is F, and U minus W is 0, right? The boundary, right? Now, I was saying that I want to say it's close to a harmonic function if f is small, right? So then that is that, right? So by maximum principle here, maximum principle, I have a harmonic function. I'm sorry, I have a elliptic equation in Laplace equals something which is 0 on the boundary. So the maximum is only controlled by f, right? There's nothing on the boundary to control it. Which means that I have u minus w L infinity is up to maybe some constant f. And just to be, I just put the full norm. And this is an overestimated. So which means that this constant has nothing to do with u. This comes to the maximum principle. By making this small, I can always ensure this is small. What that means is, for any epsilon that you give me, maybe that epsilon is epsilon, maybe I put epsilon tilde. For me, epsilon that you give me, there exists a delta, right? Such that if this norm is less than delta, then this u minus w in V1, I can make this epsilon tilde. Right? You agree? So how the proof is going to go is, I will eventually choose this epsilon, which will fix this delta. So this really should be delta put epsilon here, I'm sorry, which will fix this. Okay? So as long as I choose this in a way that does not depend on you, this will not depend on you, this will not depend on you, and I'm through. Okay? So the chain is clear, right? The dependence, constant dependence. This is how the constants depend. So now I no longer mention it. So let me remove this. Let me remove all of this. So what I want to write here is that given any epsilon positive, right? What have I shown? I've shown there exists a delta positive such that if this full norm is less than delta, then we can find a harmonic function harmonic function w such that w minus u is close as you want. Is okay? This is what I showed. This is the approximation. And this is essentially the step, I mean, a version of this will give us the step 1 regulator that I mentioned. And then you iterate all steps, then you're done. Okay, very nice. So if you've seen Schauder estimates before, you would know that if you don't do it like this, there's another way where you go through all these interpolation inequalities, and that can become it can be quite hard to follow sometimes. At least this is much easier and quicker.
So there's a bound and FC alpha now.
Yeah. So I just overestimated. What I had was F infinity was bounding it. C alpha has C alpha norm and this.
FC alpha.
C alpha I take because it's the invariant.
FC alpha will be having some number. It's not like it's very close to 0.
Yeah.
It will be close to 0.
No, I'm saying I wrote that earlier here. I can divide by it and make it as small as I want. Okay. Because it's a constant. So I just look at I had U infinity here and delta right? Okay. And as you can say, skip because I've already only said F alpha C at 0, but I think C alpha norm, but that is you can understand, right? So actually, what happens is you have C alpha in the ln norm and so on. But I'm not doing all that. I just want you can just assume C alpha. This is the smallest. The main thing is in the rescaling. So okay. So yeah. So what I've shown is I can go as close as I want to harmonic function. Okay. So now I said earlier that I can do it if I can get polynomials second order, which approximated I'm done. So the natural candidate here is look at the harmonic approximation for this, the second order approximation to the harmonic function that we have, right? Which is going to be harmonic anyway. So let P be the quadratic approximation of this. And I'm going to write W minus P is up to some dimensional constant RQ, right, in L infinity. Is this clear why? This is the second order approximation to W. Okay. And Laplace P is 0, right? Is this also clear? In the Taylor approximation, 0th order term is killed, first order term is killed, I'm left with second order terms. Second order is xi xj dij w0. Xi xj I not equals to j have opposite direction, so it's 0. So I'm only left with xi square, right? Xi square, this is a constant. So you're left with dii I w0, that is just Laplace of w at 0, which is 0. This is okay now, right? So I have this. And of course, there are some high derivatives here. But as you know, by integral express harmonic functions, they are controlled by norms of W itself, which is I put a constant there. All right. So I have an approximation for W is close to P, U is close to W. Therefore, I get U minus P L infinity VR less than or equal to some constant which has nothing to do with U. RQ plus epsilon. This is okay. Now, the very, very nice thing about this estimate is that this scale is minor. I have not specified R. Right? So as you see from here, I mean maybe this will not confuse. Maybe let's put a lambda here, put a lambda here. So this lambda I have not chosen, right? I have not decided at what scale I'll go. Right? At what rate should I go? I have not decided. So this is up to me. Now I'll decide. So since this is where I use the fact that this you can choose lambda small enough. So small enough is I think it's less than 1. Small enough. Maybe is to be small enough so that now I want so what is the rate I want? I want this rate, right? And I want to fix it. So this is the rate I want to fix. So if from here I can put out half of that, and from here I can put out half of that, and done. Right? That's the rate I put out. Such that 2 times, I take 2 to make it half, such that 2, the constant, now Now R, I'll write lambda Q is less than or equal to lambda power 2 plus alpha. Why can I do this? No matter what this constant is, okay, I can always arrange this by taking lambda small enough. Why? Because alpha is below 1, so this goes to 0 faster than this does, right? So this will anyway fall below if I take lambda small enough, no matter what how high this is, right? So I can arrange this. Once lambda, so this fixes lambda. It says lambda, and I fix it in a way that has nothing to do with the solution, right? Now I just have to fix epsilon. So then use epsilon small enough, again below 1, small enough, right? Again 2 C epsilon is less than or equal to lambda 2 plus alpha. Again, let's be clear on the dependence. Epsilon depends on C and lambda. C has nothing to do with the solution. Lambda depends on C, which has nothing to do with the solution. So this has nothing to do with the solution. Okay, it's universal. So once I do this, so if I do this, R has become lambda. So what do I get? Get that U minus, let me now just call it 1, L infinity B lambda, right? Is less than or equal to half of that plus half of that, so that is exactly. Now, it is very important that the constant here is 1, which is why I insist on putting all the 2's here, because we'll iterate. When you iterate, if you have a constant here, it'll keep power k, it'll blow up and you have nothing left. Okay. And now it's essentially like an inductor. So I've got like the first step of induction. Next step you can do. So this does it for k is equal to 1. So I have scale, I have the first scale. So that I started this scale. So take I'll mention something slightly different later. Let me now just do it directly. So take 2 plus alpha rescalings, which is what? Which is so I'll explain what is happening. First polynomial P1, lambda x. So I'm rescaling to 1. Okay, lambda x rescaling.
So in 6, lambda is not going to 0. That's not true for all.
No. This is, I've first found a scale. I found that there exists a lambda. Okay. So now I'm going to iterate with lambda per k. That will go.
Lambda is fixed now.
Oh, yeah, it's fixed, but it's fixed universally. Right? So this is what that's why I replace lambda. It's we can find, right? We can find some lambda at the scale. So I've only fixed my scale here. I've not iterated, which is why I said that the constant here better not be. I only fixed this. I found so this is your scale 1 regularity. It's like scale 1 regularity. So I set this in the W2P estimates also. I got it at some scale, and then I use the PDE now and repeat this estimate at every scale. Okay. So what should be the rescaling? So I take this rescale to 1. I go back to 1, and I should also take care of the right. Yeah. So if I do this, I'm back in B1, and what is more important is if I take Laplace of u lambda, right? This is 0 by construction. Laplace of u is f. So what do I get? I get f lambda x. If I put a Laplace, square pulls out, right? Lambda square by lambda to lambda alpha. Now this goes. So what do I get? Lambda x by lambda per alpha. Now something really nice happens here. If I did not, this is where you need the Helder cat. So far, I've never said anything about f being Helder, right? When I did this also, f was just L infinity, right? I didn't need it to be Helder when I did that approximation. I just needed L3 norm principle. This is where you need Helder. Because as lambda is going to, as there will be some power k here, as this thing is going to go to 0, this will blow up if I have no control. Right? So it is exactly here. I said that, for example, f0 is 0, I normalize. So the growth here is what? Lambda per alpha. Lambda per alpha cancels, it's a constant. Which is why f is, this is where I'm going to use f as Helder. This is C alpha and this is 0. What do you say? Okay, elsewhere I have no need, right? This is exactly why. Otherwise, the proof would go through, right? Which cannot be correct. You can't even get C2. But you just L infinity. Okay, so I've said that. Now, let's call this G, right? And as you can see, the norm of G is again at most the norm of F because this is going to go by this character, and which is anyway less than delta. So I can now, by the approximation lemma, right, I can start this process again. So apply approximation. I'll just call it a proper. You can call it many ways. You can call it harmonic replacement. You can call it approximation lemma. You can call it. So apply approximation lemma or scale or that to u lambda, right? The rescale. So I can find another harmonic polynomial, second order, which in L infinity that is P1. So P2, I'll not call it P2. So L infinity P lambda, right? Well, right? P lambda is less than or equal to constant lambda power 2 plus alpha. Now this is for a rescale function. I scale it back, right? If I scale it back, this scaling, right, will turn this into what? So if I rescale, get first of all, this lambda will rescale to what? Lambda power. Go to this rescale to lambda square, right? I'll have one more lambda. So I rescale to ux minus p1x from there minus lambda 2 plus alpha down there times let's call this p tilde x by lambda, because this was at x, I've scaled as x by lambda, right? Times L infinity b lambda got scaled by lambda, so lambda square is less than or equal to, now the denominator goes here, this becomes lambda 2 plus alpha, right? So, and this thing is minus, this is plus, I'll call this my P2, right? So I've produced you for another polynomial, right? Now you can go on, same set of process. So I've got at scale 2, now you do it at scale 3, scale k, and so you get it at scale k. So you've got this, and you're done. If you don't want to do it like this, you can also make it an inductive hypothesis, right? What I've shown here is essentially step 1 of inductive hypothesis, then the inductive step. You understand? So this finishes the proof. Okay. Now let me just say a few things.
We have C alpha not less than delta.
Huh? Because this f will only at most pull out a lambda per alpha, which will cancel this. So I'm back at fx. That's all. This is fx minus f0, right? Because f0 is 0. The lambda per alpha, so that is at most. So there's a Helder constant of f, which I've made less than this. So this g is controlled by the Helder constant of f, right? So like I said there, I don't really need the Helder constant. I just need the L infinity number. So the L infinity constant of g is controlled, which means the whole thing. I just wrote C alpha as an overestimate. Right? Okay, so this finishes this. I think we should have.
This lambda is less than 1?
Yes. Of course.
Okay.
Because see, at that point anyway I choose lambda small enough, right? Otherwise,
Yeah, I got it. Because it should be for all R.
I can't, for example, I had something higher here, right? Q, yeah, this one. This, right?
In
So
the
this, if lambda, this can never be true.
in the calculation, one needs to do it for all balls.
Right. No, so that's what I said. I said that if you have it at all scales, then I proved another lemma saying that I can get it at all. Because if you have it at RK, then you can track between this, right? Once you have this, it doesn't really matter at what scale you start, as long as you hit 0 in that at this rate, right? So you need this. Okay. So Yeah, so maybe I'll just mention a couple of points, which is that we had three estimates. For harmonic functions, right? I use this, right? I have three estimates for harmonic functions. So when you're doing it for a general operator, you have to have regularity for that operator. Next, you can put coefficients. Long as they are close. Delta I is the identity, right? So here my operator is just a Laplace, and I was perturbing with f. But if I have something like aij, okay, fij, then I fix a point, okay, maybe turn the whole thing into identity, and then I'm looking at some condition like aij minus delta ij, some norm here. I'm not going to specify small, just like I had some smallness conditions. Right? So you need this, right? General elementary purpose, of course, you can't get C2 alpha and so on, right? It's absurd. So you need some smallness, and it may be in some norm as well. Similarly, you can weaken and weaken, which I was telling you earlier. F in C alpha at 0. F in C alpha at 0 in Ln cells. So I'm not going to say more about this, which essentially something like the Ln norm is like C alpha. The n is important. N is a dimension because if you use it like this, then you're going to use the ABP. Here I just had f infinity right on the right. It was fine, but if f is an LP, then you know I need to do ABP. I need Ln there. Which is why
Ln is what?
Ln is the n is a dimension. Ln
This by Euclidean.
Yeah, LP space wala L.
Little L.
No. This capital L. Capital L. So
Alpha derivative is in Ln.
no, not alpha is. F is C alpha in the Ln sense. So there's technical definition to go. So instead of measuring C alpha now pointwise, you can measure it in an integral sense.
Alpha derivative is in Ln. D alpha f is in Ln.
No, D alpha F. That's not
The distribution set of distribution is in Ln. Is that what you meant?
It's something like the average. So the average in PR, okay, R power minus alpha. Super. This is just a technical thing. So F, I've said F minus F0, which I've kept 0. Okay. This is a dimension. F is C alpha, then this is already there at 0, but you can weaken it in this sense. But see, like I said, these are all technical things. If I have it like this, you can still do the whole thing. Except now instead of this, you use the ABP estimation.
It's kept
Huh?
for all capital N.
No, this is n is a dimension.
Okay.
Of course, we have more than n because it's going to dominate it.
It is also suppose you are thinking of C2 alpha.
No, this is C alpha.
Yeah, no, I'm asking a question.
Okay, sure. If you put like
Suppose C2 alpha is there.
then you get more regularity. So if F is C alpha, you get U is C2 alpha. If you upgrade this once more, you just keep upgrading.
My question is, like, suppose U is C2 alpha. So, and you are measuring infinity now in. Okay, so instead of that, suppose is it
No,
the
this is weaker than n. So if you have the pointwise thing, you will have this, right? Because I mean, what is this?
My question is not that. So you are taking integrability with respect to the dimension.
Yeah, the dimension is because
related with
no, this dimension is because of the ABP. You can take any p here bigger than n. You can't go below n because you will not get the ABP estimate there. You won't get the maximum principal below Ln. That's all.
No, I'm saying suppose U minus PK infinity norm you measured.
Oh, this one.
Yeah.
Sure. You instead of N infinity, there are other norms. Yes. So I was going to mention that.
Yeah. So like in C2 alpha, I can take 2 also. L2.
C2 alpha. Why would I take C2 alpha? U is not in C2 alpha, right?
No, I'm saying suppose U in C2 alpha.
Uh-huh.
Then like
You can do it. You can do it as a.
like in the L2 space we can measure it. Something is there a criteria?
Yeah, I'll come. Okay, so what I'll tell you is that, for example, if you do it for, you can do this whole thing. I did it in terms of these non-divergence thing. You can also do it for divergence PD. That's right. Yeah. You can also do it for this. Okay. And then the thing is, if A is C alpha and F is C alpha, then U is, I think, C1 alpha. Okay. You can get this also. And in this case, you won't have, there's no pointwise estimate like that. In this case, all of these will be something like U minus some polynomial in some LP norm you get, maybe L2 norm here. Less than or equal to same rates. Similar rates you have, except that since this is 1 by 2, this has to be scaled appropriately. Okay, so you can, the same theory, if I had time I could have done it, the same thing runs for divergence PD also. Okay, you can do it for this also. And here, of course, you can't measure N infinity norm, you measure it in L2 norm. Okay, or I mean, any LP on that doesn't matter. So here you'll weaken. Yeah, this is X. And here, what I was saying earlier was fx minus f0, so this is x, right? X power alpha, r power alpha, 1 by n goes. That's where f is held. This is a weaker condition. Okay. And yes, this was my next one. This was my fourth point. Which is that you can run sim arguments for this, okay, except that here the measurement will change. And this one is C1 alpha. So here also I did C2 alpha. You could also do C1 alpha. Except instead of approximating by paraboloids, you approximate it by planes. Okay, and the rate at which it goes, of course, will not be quadratic, it will be separate linear metaphor, right? I think this is all. Okay. For references, but so all that I did, the W2P estimate and the Schauder estimate, and so on, this way, I think was first done in the following paper of Caffarelli. So this is a paper. I was trying to correct it. Cite the references and like. So the W2P estimate I did in the last lecture, slightly different from what's given here. But and that I always said where you find it. But the C2 alpha estimate goes like exactly like this. Okay, because it's quite nice. So the paper is titled I just want to be it's famous here a priori estimates for solutions. There's also a Monge-Ampere paper with similar titles for solutions. Equations. This I think this was. So the W2P that I did, the C1 alpha that I mentioned, the C2 alpha that I did, earlier. Okay. This argument is verbatim whatever I've done, except he writes it in inductive fashion. This is slightly different, and for this one, like I said, I used BA1's rewriting of the and textbook accounts of all this. For this Laplace, you can find it in Mooney's notes. So Mooney has notes. These have lots of nice pictures. On his web page. So if you Google, I think you'll get it. So this has the Laplace case, for example. I took it from there. Then and Lin notes. This is the first volume. And in this one, I forgot to mention this. W2P is also there. This is also there. It's in the final. There's a chapter on viscosity solutions. So here you will find AIJ, UIJ. Okay, and the conditions that I mentioned, the ALN close and AIJ close in substance, you'll find it here. And finally, Caffarelli and Cabre. Equations. This has whatever I did for this. This has this in F. That's it. The full theory is more simplified. So that's the